Okay, we'll continue. Okay, so now next chapter, partial differential equations. Okay, so you must be familiar about this term. PDE, partial differential equation. Just now ODE, ordinary differential equation. Okay. Okay, partial differential. So normally the partial differential equation is not as like this, right? dy, not dy. Okay, differential. Okay, like this. Yx, sorry, x. Okay, just now normal differential equation we have dy dx. So this one is like a notation, something like that. Okay, so this is a partial differential equation. Okay, so there are two parts. Okay, so the first one, okay, finite difference elliptic equation. So basically, this chapter will be continued and will be used, apply in an elective course in your final year. You can choose an elective course which is called FEA, finite element analysis. Finite element analysis, FEA. Finite element analysis course. It's an elective course in your final year. Okay, you can take that course. So this chapter is going to be continued. It's going to be applied in finite element analysis. And some of you maybe will have to use we have to apply finite element analysis in your FYP, final year project. Okay, so this is very useful. Okay, so we have okay, so in this course I'm going just to introduce to you what is partial differential equations that is going to be used in finite element method. Okay, so the first one is finite difference, which is going to use elliptic equations. So elliptic equations is in engineering. Is normally used in steady state. Okay, to characterize steady state solution. Steady state means that the function is independent of time. Okay, doesn't depend on time. Okay, normally is an is ideal situation. In ideal situation, we assume a steady state solution, steady state function. Okay, means it is independent of time. Means that if dy over dt, okay, if you are dy over dt, this function will be zero. Steady state means that a difference in times is zero. The gradient in times is zero, steady state. Okay, and we'll use also boundary value problems, of course, the one that we have learned just now. So that's why we have to learn first initial value and the boundary values, and now PDE, partial differential form, partial differential equation, because we're going to apply these boundary value problems. Okay, so for numerical solution of elliptic PDE, partial differential equation, the PDE is transformed into an algebraic difference equation, and also algebraic linear equation that we have learned in chapter 1. Okay, so basically we combine all the things that we have learned chapter 1, chapter 2, or maybe not, chapter 1, chapter 3, chapter 4. Okay, now we are in chapter 5. Okay, so so we have to transform, okay, the PDE, partial differential equation, into algebraic difference equation, which is in terms of normally matrix equation, and then we are going to apply Gauss-Seidel. Okay, those that we have learned in chapter 1. Okay, so because of its simplicity and general relevance to most areas of engineering, we use a heated plate. So again, for examples, okay, we are going to see examples in terms of a heat transfer process. And most importantly, because heat transfer is my area, not my area of expertise. So that's why I will show you. I will use a lot of example of heat transfer. Okay. Okay. So we will use a heated plate as an example for solving elliptic PDEs. Okay. So for example, like this. We have like a small element here, Okay, QX, we use notation Q because Q is normally a physical notation for heat transfer. Okay, Q, so we have Q function of Y and X. Okay, for example, we have an element, a small element here. So we have QY, okay, at points Y, and Q at points Y plus delta Y, the step size, and also QX and QX plus delta X. Okay, so so this in this chapter, okay, means that we are going to solve. We are going to calculate the points, the temperature or the heat transfer at an element, okay, in an element, okay, that we are going to consider a small element. Okay, that's why sometimes it is called finite element analysis. Okay, okay. So example like this one also. For example, we have y-axis and x-axis. So we are going to we call it discretize. Okay. Or discretize, or simple words means we are going to divide, okay, the axis x and y into several nodes. Okay, this is all this black point is called nodes. So for example, we have m plus 1 nodes along the x-axis, and we have n plus 1 nodes along the y-axis. Okay, so example, we have a plate, a heated plate, okay, like this. So we are going, when we apply the PDEs, partial difference equation method, we are going to imagine that we are dividing, discretizing the heated plate into several nodes along the x and y axis, along the vertical and horizontal line. Okay, we imagine that we divide it into several nodes, I and j, that we call I and j. I is the x-axis and j is the nodes along the x-axis. So if we choose a point at the center point ij, so we are going to calculate, measure each of this node. So for example, this one is I plus 1j, this one is I, j plus 1, this one is I minus 1j, this one is I, j minus 1. Okay, so means that we are, okay, for a heat transfer process, it means that we are going to calculate temperature at each of this node. Okay, temperature or heat flux, okay, at each of these nodes. Okay, so elliptic equation, Laplace. Okay, I hope you have heard about this Laplace equation. I think in Maths 1 or Maths 2. Okay, Laplace equation is actually pronounced as Laplace. So betul saya pronounce because it is from French research. Okay, scientists. So Laplace equation. So Laplace equation is an example of elliptic equation. Okay, so just now I mentioned elliptic equation. So Laplace equation is one example of elliptic equation. So elliptic equation is this in this form. Okay, so we use Laplace equation, okay, because it is an elliptic equation. So we have Laplace equation. Laplace equation, what does Laplace equation said? It is a second order partial differential equation. For example, here t, that depends on two values, which is x and y. This is Laplace equation. Okay, so this Laplace equation can be discretized, can be developed, okay, into this form. Okay, this is like a Taylor's equation. Taylor's, I've mentioned before, previous chapters, like a Taylor's equation. So this partial differential equation can be developed, okay, into this form, second order. That's why we have here. Okay, second order. Okay, this form. So we this is from Taylor's. Okay, so if we rewrite the Laplace equation, okay, by using this definition, so we have this equation. Okay, we change the form of Laplace equation, we change it into this equation, Laplacian difference equation. Okay, this is more explanation detail. This is the calculation that I have made, just to explain how do we derive from here to here. Okay, just to explain if you didn't capture the solution. Okay, so this is like if you have a second order partial differential equation F. Okay, so we use, so second order is actually the derivation of this first order differential form. So if you use this definition of derivative equation, so we have like this from the definition of differential equation, derivative form. So second order, that's why we have h square, or in this Laplace equation, it is delta x square. This is like a step size. Okay, so this is just to explain how do we get from here to here. Okay, so we're just going to apply this in red, Laplacian difference equation. Okay, so this example of a heated plate just now. Okay, so we have a heated plate like this, square form. Okay, kind of like square form. Okay, so we have boundary values given 0 degrees, 75 degrees, 100 degrees, and 50 degrees. So these four are the boundary condition. Okay, boundary condition given at the extreme points, the 4 extreme points of the heated plate, of a plate. Okay, and we imagine, okay, we discretize, okay, the plate into here 9 points, 9 nodes. Okay, 9 nodes. Okay, we discretize it into 9 nodes. So we call it 1 position. The position 1 means the x1 y1. Not x, ij just now. We use ij. So I1 j1, I2 j2, I2 j still j1. Okay, I3 j1. Okay, etc. Along the x and y axis until 3 3. Okay, so this must be I3 j3. Okay, so imagine these nodes. Okay. In addition, boundary conditions along the edge must be specified to obtain a unit solution. Okay, so we have boundary condition. Okay, the boundary condition is set. Okay, a fixed value. Okay, so for example, okay, example for node 1 1. This one. For this node, example. So we apply the Laplacian difference equation just now. What does Laplacian just now? Set ti plus 1 j, ti minus 1 j. Okay, we try to do. Okay. Okay, the Laplacian difference equation, ti plus 1j plus ti minus 1j plus ti j minus 1, j plus 1, ti j minus 1, minus 4tij. Minus 4tij equals to 0. Okay? So we are going to use this Laplacian difference equation for node 1 1. Okay? So 1 1, 1 1. Okay, so ti plus 1. So ij is 1 1. Ij 1 1. Okay, so ti plus 1. So that's why 2 1. Okay, I plus 1, so 2 1. So we have p I minus 1, so 0 1 plus ti 1 2, J plus 1, plus T1, 0, minus 4, T1, 1 equals to 0. Okay, sama So that's why we have this. A balance for node 1, 1. T21 plus T01 plus T12 plus T10 minus 4 T11. Okay? And with the boundary condition values given, so we know T01 is 75 degree just now. This 75 is along x equals to 0 axis. This we imagine this line is the x equals to 0. Okay, along this line is x equals to 0. So whatever values of y or j, okay, as long as the x is 0, so the temperature value is 75 degree. So that's why we know this condition 0 at 0, okay, is 75. So as long as we are in this boundary condition, T01, T01, T02, T03, we will have values of the value is 75 degree. Okay, so T01, 75. And another boundary condition that we know is T10. Where is T10? T10 is here. Okay, along the line where y is 0. T10. So T10 is 0 degree, T20 is 0 degree, T30 is 0 degree because it is the boundary condition. Okay, so that's why we have T10, 0 degree. Okay, so those are boundary condition values that we know, that we are given. Okay, so we can simplify this Laplacian equation for node 1, 1 into this form. Minus 4 T11 plus T12 plus T21 equals to 0. Okay? Not equals to 0, 75. Pergi situ Okay, 75. Okay. Okay, so if we apply this Laplacian equation for all the nodes, 1, 1, 2, 1, 3, 1, for all the 9 nodes, okay, we will get a set of differential, a set of algebraic equation, okay, or a matrix equation. This one equals to 75, bukan 0, 7 equals to 75. Okay, so we write it in like a linear algebra equation, or it's like a matrix, okay, matrix form. Okay, so if we apply the Laplacian differential equation for all the 9 nodes, we will get this set of 9 simultaneous equation of 9 unknowns. We have 9 unknowns because we have 9 nodes just now. Okay? So that's why in the beginning I mentioned that we will apply all the previous chapter that we have learned. So now we come to this algebraic linear equation. Okay, so Liebman method. Liebman method is actually Gauss-Seidel method. So it's nothing new sangat. Okay, most numerical solution of Laplace equation involve systems that are very large. Okay, this example is just 9. So sometimes you can have more bigger, okay, large solution, large equation. For larger size grids, a significant number of terms will be 0. Okay. Means that if you have higher values, unknowns values, we will have more 0. So all of these are 0. 0, 0, 0, 0, 0. Okay. For such a sparse system, most commonly employed approach is Gauss-Seidel. Okay, so Gauss-Seidel, the one that we have learned in first chapter. So which when applied to PDE is also referred as Liebman's method. So it's actually, Liebman method is actually a Gauss-Seidel method that is applied to a PDE equation. Okay. Okay. So when we mention Liebman's method, it's actually Gauss-Seidel method. Okay. So how to solve this is the same as we solve linear algebra equation. Okay. Okay. So this example, I think I have. Saya dah calculate. Okay. Okay. You use Liebman method to solve for the temperature of the heated plate. Okay. Employ over relaxation with a value of 1.5 for the weighting factor and iterate to epsilon 1%. Okay. So, wait, I think I choose window form. It will be bigger. Okay, sekejap present now. You want touch screen? Okay. Tak tahu lah besar ke tak. It's slightly bigger. Okay. Okay, so this one I have done the calculation. You can look at it later on. Okay, I just going to explain. Okay, so we have the example or this notation tau, we call it tau, is the over relaxation given, which is 1.5. Okay, over relaxation means that we try to attenuate, okay, to stabilize the calculation, because we're going to calculate several times, several rounds. Okay, so we are going to stabilize the solution that we get. So we have a parameter that we call over relaxation parameter, which is here is given as 1.5. Okay. Okay, and the epsilon, the difference is 1%. We target to achieve a 1% error. Okay. Okay, so this is the equation, the Laplacian equation just now, just that here divided by 4. Okay. At I1 and J1, ini besar lagi okay. At I1 and J1, okay, so T11, okay, I1, J1, T11, so we apply the Laplacian just now, okay. What do we have? We have T01 just now 75 degree boundary condition and T100 degree Celsius. The boundary condition the same as just now. Initial temperature for the plate is 0 degrees Celsius except for the boundary condition. Okay. So here is a assumption that we made. I think assumption that we made that we assume that the initial values of temperature of the plate is 0 degree. Other than the boundary condition given. So means that the heater plate just now, this one, okay, other than the boundary condition, the other points, the initial point, we assume it is, means that T0, initial point is 0 degree. That is an assumption that we made, okay. Okay, so T11, okay, to calculate T11 at I1 and J1, so T0, T21, okay, T21, 0, okay, T21, 0, the initial point that we assume, okay, plus T01 is 75 degree, T12 and T10 is 0, 0, okay, the boundary condition and the one that we assume. So we have T11 is 18.75 degree. Okay, and then if we apply the over relaxation just now 1.5, okay, to differentiate, okay, the values of new and old value. Okay, so we have T11, the new value of T11 Okay, this is the new value 18.17 and so we have 28.125 by using this overrealization. If it's given, then we just use it. Okay, so we have T11 28.125. Okay. Okay, so for I, okay, next we do the same for I equals to 2. Just now I equals to 1. And then we repeat again the equation for I2 and J1. Repeat again. So we have T21. So use the Laplacian differential equation. Divide by 4. Okay. So we have this 7 degree. 10.54. Okay, 10.547 degree. And then I3, the same thing. Okay, I3, and then we get 22.7. Okay, so we do the same for I1, I2, and I3 for the heated plate. Remember the heated plate just now. So we have I1, I2, I3. For J equals to 1. Okay, so we have the value T11, T21, and T31 for first round, only for first round. Okay, and then and then we have to do the same for T21. Okay, or T12, whichever point you can you do. Okay, so T12. Okay, T12 means this point. Okay, first round we calculate T11, T21, and T31, right? Okay, so now we proceed with T12, T22, T32, and then next T13, T23, T33. Okay. Okay, so the same method. Okay, apply the Laplacian and calculate T12, T21, T22, T23. Okay. And then for the third line, okay, 3. Okay, after that, we to calculate the error, okay, the error. So we use, for example, for at point T11 just now, I and J equals to 1. Okay, our new calculation was second iteration. If you do second iteration, we get 32.52 minus the first iteration, which is 28. Okay, times 100%, and we get the error epsilon 13.5%, which is still higher than 1%. So means that we have to continue the calculation for the next iteration, for next round. Okay, so this type of problem, okay, it's actually computation is continue until 9th iteration. So until 9th iteration that we achieve an error epsilon less than 1%, which is 0.71%. So it takes a long time, okay, to calculate manually. So I just calculate until second iteration, just to show you the steps. Okay, so for each point of the node, for example, here we have 9 nodes. So we apply the Laplacian differential equation, and we calculate for each point. Okay, and we continue iteration. Okay. Okay, and this one. Okay, so this one you can do by your own self. Okay, the same problem. Okay, but we're not going to do the now. You can do it as homework. Okay, use Lippmann's method, means the same method as just now, to solve for the temperature of the heated plate, but with the upper boundary condition increased to 120 degrees Celsius and the left boundary decreased to 60 degrees Celsius. Okay. Employ overrealization with a value of 1.2 for the weighting factor and iterate to epsilon 1%. Okay, so you can try this one as your homework. Okay, exercise. Okay, just that we change the boundary condition this time. Okay, so the upper condition just now, change it into to 220 degree, and the left boundary, which is just now was 75, right? So now decrease it to 60 degree. Okay, and then try to solve the problem. Okay, so this one you can try by your own self. Okay, next. Okay. Okay, boundary condition. Okay, sometimes the boundary condition is given in terms of differential form. Okay, like this. Because just now we have boundary condition like just a simple parameter like temperature 75 degree, temperature 100 degree, like that, right? Okay. Sometimes we are given boundary condition in terms of a partial equation, which is in heat transfer process, the partial equation is normally the heat flux. Okay, so for the heated plate problem, sometimes heat flux is specified at the boundary rather than the temperature. So this heat flux is in terms of a differential equation. Okay, and if the edge is insulated, means the bond, if the extreme point at the extreme point is insulated, means that this derivative, this heat flux becomes zero. Okay, so if the plate is insulated at the extreme point, okay, for example, the left hand side is insulated, means that there is no heat transfer process occur at the left hand side. Okay, if the heat plate is insulated, okay, insulated means that we put a material that with no conductivity or with a very minimal conductivity, means that heat transfer process cannot occur at the extremity, okay, at the boundary, because we insulate it with a material, so something like a foam, okay, that cannot that conduction process cannot occur. So at this point, we call it, okay, that the heat plate, the edge of the extreme point of the heat plate is insulated. So when it is insulated, means that there is no heat transfer process occur, or the heat transfer process is very minimal. So it means that the heat flux, no heat transfer process, so the heat flux is zero. So that's why it means, that's what it means by this. Heat flux zero, the heat flux is the in terms of derivation, so this derivatives become zero. Tak faham ke tak? Okay. I draw. Sometimes the boundary conditions, okay, the one that we have seen just now, the boundary condition 100 degrees, 75 degrees, 0 degree, 100 degrees, something like that, right? Sometimes the boundary condition is given in terms of a partial differential equation. So for heat transfer process, the partial differential equation is usually the heat flux. So it is given sometimes in terms like this. Delta T, the partial differential dt dx. Okay, so this is actually a heat flux. You know that, like this. So if the plate is insulated, okay, means that is an insulation material is placed beside it. For example, in insulation material, something like a foam that cannot conduction process cannot occur. Okay, so the heat flux here, there is no conduction, okay, between the two material. So there is no heat flux, then there is no heat transfer process occur. So this heat flux will become zero. So we know that the boundary condition at these points is zero. That's why that's what it means here. This derivative becomes zero. Okay?
Okay, doctor.
Okay. Okay. Wait. Okay, for example, this point, okay, so we have T0J, T1J, T0J. Okay, so because this is at the boundary condition at the edge, so we assume an imaginary point, okay, imaginary point outside the plate at x minus 1. Okay, this is just an imaginary point. Okay, so this is the Laplacian differential equation just now. Okay, so this Laplacian equation is applied for this point T0J. So now we have an imaginary point which doesn't exist at T minus 1J. Okay, so this T minus 1J, okay, if we use the definition of derivative definition, so we can write this T minus 1J in terms of this, okay? So now we have a heat flux or a partial differential form in the Laplacian equation, okay? We replace the imaginary point with this differential equation. So now we have this derivative incorporated into the balance node. Okay. Okay, so so this example equation, if we are given a heat flux or a partial difference equation condition for the boundary, okay? Another example of boundary condition is that we have irregular boundaries. Okay, sometimes the problems that we have, the boundaries is not a normal boundary, okay, like a rectangular, a square form. Sometimes we have a curve like this, okay. So this is irregular boundaries, which is we have to assume, okay, the x, okay, the x and the y, delta y, delta x, okay. Okay. I think it is explained here, the calculation. Okay. Okay, so again, with the Laplacian definition, we have to substitute these irregular boundaries, okay, in the Laplacian equation. So this is how the calculation is made. Okay, I explain here. So we have this, the second order Laplacian just now, the second order heat transfer equation just now, we can write it in terms of this. If we have irregular boundaries, alpha is the parameter, a constant. Okay, so if you have irregular boundaries given, okay, so we develop the Laplacian equation just now, and we get this, this form. So a new form. Okay. Control volume approach. Wait, I see. So this is example like I have drawn here. Okay. Imagine material B is the plate, the heated plate that we have, and at one edge, at one extreme point, we have an insulated material, which is material A. Okay. So this part, we assume this boundary, this extreme point is insulated. Okay. But the rest here, still heat transfer process can occur. Okay. The control, okay. Okay. Next one. Okay, today we are going to exit until we're going to do class until 4 p.m. Okay, finite difference. Okay, another equation is a parabolic equation. Okay, just now is elliptic equation. This one is parabolic equation. Okay, why we have to introduce parabolic equation? Parabolic equations have to be are employed for time variable, unsteady state problems. Okay, remember just now elliptic equations is applied for steady state, means that the function is independent of time. steady state, which is normally the ideal process, the ideal solution. Okay, this time we apply parabolic equation to a characterized time variable, variables, unsteady state problems. Okay, means that the problems, the experiment or the process depends or change in time. Does change in time. Okay, so example, conservation of energy. Equation of conservation of energy is an example of unsteady state energy balance equation. Okay. So again, we have a rod from hot to cool. Okay. Example of parabolic equation or unsteady state equation is the Fourier's law of heat or conduction. Okay, so this equation is used, is applied in the thermofluid lab 3 equation experiment. Okay, so heat conduction equation, the heat conduction equation is this one. Okay, those who have done the experiment, the lab 3 experiment, so the answer to your experiment, so it's we apply this heat conduction equation, okay, the Fourier's law. It is called Fourier's law. Just now Laplacian law, Laplacian equation. This is Fourier's equation. So we can see here that the temperature depends on time. This function is not zero. Unsteady state means that this function has a value. Okay, it's not zero. If it's steady state, then we can assume this differential is zero. So we have the heat conduction equation. K is the thermal conductivity. Okay, it's a parameter. Depends on the material. Okay, T temperature, X is the distance along the rod, and T is time. Okay, just like the elliptic equation, parabolic equation can be solved by substituting finite divided difference for the partial derivative. Means that we divide it into nodes like just now. Okay. So parabolic, just that parabolic equation PDEs are temporarily open-ended and involve new issues such as stability. So there are four parabolic equation. There is problem of stability, means that the solution sometimes cannot be stabilized, change very quickly. Okay. So here, so it gets more complicated because now the heat plate, the heat transfer process depends on time. So we have another parameter, another unknowns value, another axis, okay, which is times, depending on time, x, y, and t. So here the node for times is written in L. So L is the time, and I is still the distance x. Okay. So imagine we discretize the heat plate into these nodes. Okay. In x and t times. Okay. So in order to solve the parabolic equation, okay, the heat conduction equation is the parabolic equation just now. We have two methods, explicit and implicit method. Okay. So explicit method. So this is the equation. Okay. Just like just now the Laplacian equation. Okay, so explicit method, we have the second order partial differential t over s. So this is the same. It's just that this time we have this L. Okay, this unknown value L. L is the times. So time at L second, for example. Okay. So now we have two unknowns. Okay. So and then another one, derivative of t over time, okay, unsteady state. So it is written as like this, okay. For time, I is the same, L different. For x, distance, I plus 1, I, okay. This is the same as Laplacian just now. So if we substitute these two forms in the heat conduction equation just now, Fourier's, this one, the Fourier's equation. So we substitute this one here and this one here. Okay, so we have this equation. Okay, with lambda is k delta t delta s square. Okay, lambda. Okay, this is the explicit method. Explicit method, okay? Okay, explicit method. Okay. All interlinear, okay? So we apply this explicit, like just like the Laplacian method just now. So we apply this explicit method for each nodes. Okay, this is just graphic, just so that we can understand better. Okay, if we are going to apply the explicit method just now, for in terms of times, the values that are going to the point that we are going to consider is this point and the above it. Okay, for space difference, okay, which is the distance x, we are going to apply this point, this point, and this point. This is just a graphic explanation to explain this this method. Okay, so for just now the x, okay, the x which is I distance, okay, for each point I, for to apply this method, we have to know the values of I plus 1 and I minus 1. I plus 1, I minus 1. So that's why here, the circle, the grid point involved in space difference. Okay, means for each point I, to calculate the explicit method, we have to know this point, and this point. Okay, for space difference L, okay, for to apply the explicit method, we need only point L and point L plus 1. Point L and point L plus 1. TL and TL plus 1. Okay, so this is just a graphic explanation of the explicit method. So for this one node, we have to know each of this point. Okay, so exercise 2, okay, I have an example here. Okay, exercise 2 example. Use the explicit method to solve for the temperature distribution of a long thin rod. So again, we have a thin rod with a length of 10 centimeter, and the following values: k is given 0.835 centimeter square per second, delta x 2 centimeter, delta t 0.1 second. So at the initial point t0, the temperature of the rod is 0. So we assume at initial point 0, the rod, okay, is at 0 degrees Celsius. Okay, except for the boundary condition which are fixed for all times at t at 0 100 degrees. So this is the boundary condition, and at t10, the final point TL10 is 50 degrees Celsius. Okay, so means that sikit lagi nak habis this is just less than 10 minutes. Okay, please bertahan. Okay, so we have a rod. Okay. Okay, what does it mean here? So T0, this is X0, T0, 100 degrees Celsius. So X10, T10, 50 degree Celsius. And at the same time, we know that the temperature of the rod is 0. Okay, at T0 seconds, the temperature means that at initial time, not the initial point at 0, initial time, at the beginning, the rod, okay, all along the rod is assumed to be Tx, initial 0, or like this, 0, okay, the time 0, is 0 degrees Celsius. Okay, so that's what it means by it. At T0, the temperature of the rod is 0, except for the boundary point. This boundary point, okay, boundary point 1 degree 50 degrees Celsius, except at those extreme point, we use the boundary condition given. But for the rest, example x1, x2 meter, x3 meter, until 10 meter, until 9 meter, 9.999 meter, the initial temperature is 0 degree. Okay? Okay. So if we understand the problem, then just is just the method of calculation. Okay. So this is the explicit method equation just now that we have. Okay. So at t 0.1 second, because delta t is 0.1. Okay. For the node at x 2 centimeter, because delta x is 2 centimeter, so we means that for this problem, for this exercise, we have to calculate until t5. Okay, because the step size is given as 2 centimeter, so we have to do a calculation until t5 to reach 10. Okay, so so first is so t1 is actually at x 2 centimeter, so t5 will be at x 10. So t1, okay, first t1. So t1, apply this explicit method and we calculate the lambda. So lambda is a constant value. So we apply t10, okay? T10 means that at 2 centimeter, T10 means that 2 centimeter, example here, 2 centimeter. At 2 centimeter, but at the initial point, 0, okay, of the road, so it is 0. That's what we see here, okay? And then this is lambda, T200, the same definition here, minus 2 to T10 is 0, okay, same thing, plus 100, okay, because this is the point of this boundary, T00, okay, 100. So except at the boundary condition here, at the extreme point, this is given as 100 degrees Celsius, this point. Okay, so we have T11, 2.0875, okay. T11 ni, this T11 means that T temperature for at 2 centimeter and at 0.1 second. Okay, so we have to do the same thing for X46A, 8. Okay, 468 centimeters means that at 0.2, 0.3, 0.4, 0.5 is the 10. Okay, so we calculate this. We use the explicit method, calculate. Okay, so we have until here. Okay, and then we repeat the same thing for t 0.2 second. Okay, t 0.2 second. Again, we calculate t21, t12, sorry, t32, t22, t32, t42. So we have all these answers. Okay, you can try later on. Okay, so we repeat it. Actually, in this problem, it is not given how many times we have to repeat. So just do. I just show example until 0.2 second. Okay, because it's not stated until t until what. Okay, so 4 minutes. Okay, so convergence and stability. Okay, this is just a parameter. What does it mean here? Okay, convergence means that as ds and dt approach 0, the results of the finite difference method approach the true solution. Stability means that errors at any stage of the computation around. Okay, I hope that you understand well the difference of the meaning of convergence and stability. Okay. This is just a theory part, means that when we say convergence, graphic like this. For example, we have this is the exact solution. Okay, when we say convergence, means that we are trying to approach the exact solution. whether whether our method approach or not the exact solution, converge or not to the exact solution. Okay, if we say stability means that even though sometimes we have approached the exact solution, but our solution keep changing. If we draw the graphic, it's like this. Even though we have come to the exact solution, but the solution keeps amplify like that. Okay, so that means stability means that our function is not stabilized. So sometimes that's why we introduce a parameter like lambda, k, or whatever parameter just now to attenuate our solution, to stabilize. Okay, so that is a theory part, okay, of the difference between convergent and stability. Why we need those parameters. So okay, example like this. At P6 we have a solution like this. Okay, sama je. Okay, what else? Derivative boundary conditions. Okay, tak penting sangat. Okay, implicit method. Okay, just slightly different. Okay. In implicit method, just not explicit method. Implicit method, we advance the time interval at point L plus 1. Okay, just now explicit we use the time L. Now we need calculation to calculate the temperature at time L plus 1 for implicit. Okay, this one. Okay, this is this is the implicit method equation. So means like this. For explicit just now that we have seen just now, we need to consider this point, right? Like the graphic I've shown just now. For implicit method, we consider the point at the space the time at point L plus 1. Okay, the same equation of parabolic is used. It's just that now we need to consider the temperature at node L plus 1. That is the difference between explicit and implicit method. It does affect the solution. The solution differs a bit. Okay. So what I want you to do, okay, final last slide. What I want you to do is that repeat, okay, use the same problem as exercise 2, explicit problem just now, but here you use the implicit method. Okay, use the simple implicit finite difference approximation to solve the same problem as exercise 2 until 2, okay, just until 0.2 second, means just 2 rounds. Okay, 0.2. So this one, the example that I have shown, the calculation that I have done, this is the explicit method. So you do the same, but you use the implicit method. So the implicit method just differs for the point L. We calculate at L plus 1. Okay, so just that. Okay, try to repeat this example by using implicit method. Okay. Last. I give you assignment. assignment. So not finished yet. Assignment. Okay, this one. Because actually, if you look at the calendar, okay, so week 10 is for your time to do assignment, and week 11, 7th June is actually a public holiday. Okay, 7th June is public holiday, so that's why I combined these two chapters. And because of the chapter 4 is very small also. The previous chapter is only a small chapter, so that's why I combined both. Okay, so this the assignment. So you have like 2 weeks free. Okay, not free. Okay, it's 2 weeks to do to exercise and do this assignment. The third assignment. So this assignment involve the chapter 3, initial value problem actually, the Runge-Kutta method, okay? So Runge-Kutta method, a ball at 1200 Kelvin is allowed to cool down in air at an ambient temperature of 300 Kelvin. Assuming heat is lost only due to radiation, the differential equation of the temperature. So we have the first order differential equation. So use this equation to find the temperature at T 480 seconds using Runge-Kutta second order. So only second order. Okay. Assume a step size of H 240. So second order. So only 2.240 and then 248 until 480. Okay. So the same instruction. The assignment need to be done in group, no in pair, in group. The total mass, etc. Same thing. Okay, so I give the deadline 87 June, 2 weeks from now. Okay, so that's it. So this is actually assignment for third chapter, not today's chapter. Okay, so I will upload this in Putra Plus. Okay, so last one, attendance. Wait. So I stop first sharing. Okay. Sorry that I sit a few minutes. Attendance mana ni? Okay, this one. Okay, stop recording first.